afternoon, everyone. Welcome back. Thanks for joining us. We're glad that you're here. I'm Steve.
And I'm Scott.
And together with Backyard Musings, the Science and Technology channel.
Yeah, and we're talking about a space topic this afternoon regarding the Earth and its magnetic field. So,
Earth science. Here we go.
Yeah, big science topic. So, here we go.
Earth's magnetic field, the invisible shield that protects the planet from charged particles streaming from the sun, is powered by a churning ocean of molten iron hidden thousands of kilometers beneath our feet. Although this deep interior is inaccessible, its slow-moving currents leave subtle fingertips in the magnetic field above the Earth. A new study has now revealed that one of those currents behaved in a way scientists did not expect, abruptly reversing direction beneath the Pacific Ocean and providing fresh clues about the hidden engine driving Earth's magnetic field. Would you like to know more?
The discovery challenges the long-standing view that large-scale flow in the outer core changes only gradually over the decades. By combining nearly 30 years of ground-based measurements with satellite observations, researchers reconstructed how a vast region of liquid iron suddenly changed course, offering one of the clearest views yet of the dynamic processes unfolding roughly 2,200 kilometers or 1,370 miles beneath Earth's surface.
In 2010, a broad region of iron-rich fluid deep beneath the equatorial Pacific switched from moving weakly westward to flowing strongly eastward. Scientists still do not know what triggered the reversal, but newly analyzed data from the ESA SWARM and CryoSat missions, together with observation for the German CHAMP and Danish Ørsted satellites, allowed researchers to examine the event in unprecedented detail.
Published in the Journal of Studies of Earth's Deep Interior on May 6th of this year, the study combined satellite observations with ground-based magnetic measurements spanning from 1997 to 2025. The findings suggest that Earth's outer core may be considerably more dynamic than previously thought, raising new questions about how the planet's deepest layers interact and how the magnetic field evolves over time.
And Scott, I want to add right here that they probably elicited the help of Bigfoot to set the sensors and gather data in remote areas.
Okay. Bigfoot enters into the Earth's magnetic field.
Scientists had previously viewed the outer core as a system with relatively stable movement. This major shift suggests it's, I just thought of a whole clan of Bigfoot reversing direction and running in the other direction.
Would they be called Bigfoots or Big Feet?
No, I don't know. It's like Kansas City Chiefs or Kansas City Chiefs. I don't know. This major shift suggests its circulation can change much more abruptly than expected. The study offers new clues about the turbulent processes that create Earth's magnetic field and may point to connections between motion in the outer core and changes taking place even deeper inside Earth.
Frederick Dahl, lead author of the study, explained that the model used in the research suggests that the Pacific eastward flow has weakened since 2020, adding, quote, "The rise of the strong eastward flow in the Pacific is contemporary with a change in behavior in the inner core, as inferred from geodesy and seismology. And we hypothesize that these changes in the deep interior are associated with the changes in flow beneath the Pacific," unquote.
So I'm also going to add here that geodesy is the human effort here and seismology is the Bigfoot effort here. Okay. Earth's magnetic field comes from motion in the liquid outer core, where electrically conducting molten iron moves around the solid inner core. This process, known as geodynamo, I'm not making that word up, is always changing, although many of its larger flow patterns have seemed fairly persistent across decades of observation.
ESA launched the 3 Swarm satellites in 2013. Each carries highly sensitive magnetometers that can map Earth's magnetic field with exceptional precision. Because the satellites fly in carefully coordinated orbits, they can help separate magnetic signals from the core from those produced by the crust, oceans, ionosphere, and magnetosphere. Hey, speaking of that, have you ever seen this is way off topic, but a drone, what do they call it? Instead of having fireworks, these guys had drone shows. You ever seen them?
That lit up in synchronized colors like the American flag and
Yeah, words and
stuff.
colors. Have you ever seen one of those?
No, that would take a lot of AI computer programming to get each drone in its right position with the right lights.
Yeah, you got to check it out. There's a few of them on YouTube, and I happened to watch one because I was intrigued. I didn't even know that they were around, but I watched one it was an alternative for 4th of July fireworks, and it was pretty fascinating. So
yeah, I'm going to check it out. It sounds fascinating.
Yeah, back on topic. Sorry.
Those measurements allowed researchers to reconstruct changing flow patterns at the boundary between the core and mantle. They also helped identify the sudden changes linked to the Pacific reversal and the 2017 geomagnetic jerk.
According to ESA's Swarm mission manager, Anja Strom, the long-term data set from Swarm was important to the study. She noted, although Swarm was launched after the dramatic reversal event of 2010, it has provided high-precision data that tells us about Earth's inner core in the period that followed.
Satellite observations also help researchers spot wave-like accelerations in rapidly shifting flow structures that could have been lost in noisier data sets. The study further indicates that the eastward flow may now be weakening after reaching a peak several years ago, which raises the possibility that the reversal was a temporary oscillation or part of a longer natural cycle in core dynamics. Wow, that is way...
Oh, come on. Really?
I mean, how do you study the core when you can't get to it? You're just building computer models and hoping
AI,
that...
right? It's all AI. These processes happen far beneath Earth's surface and do not threaten people or the climate. Even so, they are essential to understanding how the planet functions. Motion in the liquid iron outer core generates Earth's magnetic field, which helps protect the planet from charged particles streaming from the sun. Is this not just... This is just another evidence of a higher power, right?
Cannot happen by chance. Otherwise, every planet out there would have magnetic spheres,
Exactly.
And it's molten iron going around a solid core, and then
in motion,
and then you got the mantle and the crust, and above it, it's not by chance.
Yeah, it's like a motor, right? It's like a motor, the moving parts inside of an engine. It's just fascinating. Without that shield, Earth's atmosphere and technological systems would face much greater exposure to harmful solar radiation. There you go.
Earth's magnetic field is constantly evolving. As flow in the core changes, the field slowly shifts as well, with effects that matter for navigation systems, spacecraft operations, and models of near-Earth space weather. For that reason, understanding changes in the core is important both for basic science and for practical applications.
Okay, according to Elisabetta Iorfita, oh my gosh, ESA's Swarm mission scientist, the Pacific reversal challenges the idea that the outer core is mainly controlled by stable westward circulation. She noted, this study shows that regional changes can emerge rapidly within just a decade. The findings may also help scientists investigate possible interactions between Earth's outer core, inner core, lower mantle, and therefore give more insights into the core mantle boundary, which is a critical region for deep Earth dynamics. These people are like ultra smart. That's all I got to say. Fascinating.
Yeah, it is fascinating.
But yeah.
All right, folks. Thanks for joining us. We'll see you tomorrow.
Tomorrow. Yep. Take care, everyone. Thanks.